All right, I had another question about area between two curves. These functions look like this: 2x over x squared plus 1, and the other function is x cubed. And so I'm going to set them equal to each other to get started here. Um, this one here, if I tried to solve this just by multiplying both sides by x squared plus 1, I'd have 2x equals x cubed times x squared plus 1. This might be hard to solve by hand. I'm going to give it a shot for about 15 seconds and see how that works. So I'm subtracting 2x from both sides, and then I'm factoring out x. So there's now x squared times x squared plus 1 minus 2. Because both of those terms have an x in common. And then I can distribute x to the fourth plus x squared minus 2. And then I can factor the inside to be like, I guess, x squared plus 2 times x squared minus 1. Because I just thought of that as if it was a quadratic. I thought of that as x squared plus x minus 2. And so I needed two numbers that multiply to make negative 2 and add to make positive 1. And so that's where I came up with those. And so this tells me that we have three potential candidates: x equals 0 and x squared equals 1. So x equals positive or negative 1. I'm kind of suspicious of three different answers here. If I plug in x equals 0, I can see that we have the red value is equal to 0 and the blue value is equal to 0. So that one checks out. Let's try x equals 1. If I try x equals 1, the red value is 2 over 2, and then the blue value is also equal to 1. And if I try x equals negative 1, it also works out. Okay, so I was suspicious, but it actually works out that they have three different regions. Great. Okay. So then we need to figure out not three different regions, three different intersections, which makes two different regions. So we got to add those two different areas here. We got to figure out who's on top and who's on bottom. Okay. So the first region is going to be between -1 and 0. Let's see if there's an easy way to tell who's on top and who's on bottom. I could look at a graph, or I could choose a value to plug in. Let's try plugging in -1/2. If I plug in -1/2, then my red becomes -1 over a fourth plus 1. So I guess -1 over 5/4, -4/5. 4/5. And if I plug in -1/2 to the blue one, then the blue one is -1/2 to the third power, -1/8. And that is a smaller absolute value, but it's actually a bigger number. So I should have written this in the blue color. So this is a closer to the x-axis, is maybe easier to think about it. Okay, and so blue's on top. So we're going to go x cubed minus 2x over x squared plus 1 and dx. So we get x to the fourth over 4. And this right here is a u substitution, x squared plus 1. So du is 2x dx. And that takes care of the entire, see how du takes care of the entire numerator there. And so I just have the integral of 1 over u, which is the natural log of u. So the natural log of the absolute value of x squared plus 1. And those absolute value bars are irrelevant because x squared plus 1 is always positive anyway. Okay, I'm going to remember this because I'm going to need this antiderivative again when I do the second region. So let's plug in 0. And when we plug in 0, we get 0 over 4 minus natural log of 0 plus 1. That's a big fancy way of saying 0. When we plug in negative 1, we get 1 over 4 minus natural log of 2. So the first region has a value of that double negative makes a positive natural log of 2 minus a quarter. So this is the area of the first region, R1. Okay. For the second region, the two functions are going to switch places. If I plug in positive 1/2 instead of negative 1/2, I'm going to go up here to the top left corner. This is positive 1, positive 1, positive 4/5. And if I plug in positive 1/2, I get positive 1/8 for the x cubed. So they switch places, and it's red minus blue. So for R2, when I do my antiderivative, my natural log is in the first position, and my x to the fourth over 4 is in the second position, and I'm going from 0 to 1 instead. And this is going to come out to be the exact same thing as before. I wasn't certain that they would come out to be the same. I can't just assume that they're symmetrical, and I wasn't able to visualize these graphs well enough in my head to be certain that they're symmetrical. So anyway, those two values add up, so the total area is just 2 times natural log of 2 minus a quarter. Or if you want to distribute the 2, you could say that's the natural log of 4 minus a half, because multiplying a natural log can be the power on the input. So there you go. Please let me know if you got any questions. There's another finding the area between curves.